Hello everybody and welcome to Power Test webinar on AC Regenerative Testing Solutions. My name is Peter and I'll be your host for today. As we move through this presentation, I encourage you all to ask questions via the GoToWebinar chat feature and stop us if anything needs any further clarification. We're going to be moving this along at a pretty good pace, so if we're moving too fast, just let us know and we'll slow it down for you. At Power Test, our motto is we make it better, and we do that in three distinct ways. One is we make it better for our employees, two for our community, and three for our customers. And for our customers, our goal is to make your testing easy. Our presenter today is Rob Kazmier. Rob's a senior sales engineer with Power Test in the Custom Engineered Solutions division. Rob, can you tell us a little bit about yourself and your experience with Power Test?
Thanks, Peter. I've been with Power Test a brief 6 years, but I've been in the Dynamometer and the test industries for going on 20. Been involved in many different technologies as technologies enhancements have been made in the testing industry. So in general, I've got a mechanical engineering background, but I've been in sales, visiting our great customers around the world for many years.
Wonderful. Tackling the agenda for today. First, we're going to give you a little bit of an introduction to Engineered Solutions and Power Test. Then we're going to discuss some of the different testing technologies that we utilize here. I'm going to use that to set up the differences between what we typically use and AC Regenerative Technology. Then we'll move on and Rob will continue to give us some education on how AC Regenerative Technology is implemented and some of its key features. And then finally, we're going to look at some of the applications. Custom Engineered Solutions is a pretty broad field. Power Test offers a number of standard products, but Custom Engineered Solutions will really dive in depth and tackle specific challenges that our customers are facing. Outlined here are just a couple of examples of some challenges that Rob's tackled over the years. If you'd like, after the presentation, we have specific examples for both, and if you have any questions, feel free to reach out to Rob after the presentation. So, what do Power Test standard products test? Typically, we're featured prominently in 8 distinct industries outlined here: construction, power generation, mining, transportation, military, marine, oil and gas, and then through our Stuska division, racing and high performance. We have over 50 standard products, and these are represented in over 80 countries worldwide. And the majority of these products rely on one of 2 loading technologies, these technologies being water break and eddy current. And now I'm going to turn the presentation over to Rob, and he's going to give you some examples and a little bit of a description on each of these technologies. Rob, let me know. You should have control over the presentation now. Let me know if this is working for you.
You tell me, Peter. Does my screen show?
Yes, sir.
So water break technologies, some of the older and most proven technologies for loading a rotational device. Power Test manufactures multi-rotor water break dynamometers as a standard product and puts dozens of these machines out probably monthly almost, depending on the month. The range in size on these can range anywhere from, on the small end for a water break, 500 horsepower up through, on the largest machine that we make, it's 10,000 horsepower that it can continuously absorb. Ultimately, a water break uses water shear and momentum transfer to create the load simply by heating the water and varying the water flow through the water break in order to increase or decrease the load with the closed loop control system. Water breaks, again, depending on the size, can be used for very, very large diesel engines with a lot of torque down through high speed. For example, our Stuska division manufactures a high-speed water break that can go to 12,000 RPM to test high-performance engines or turbine engines that need to have that speed, typically with a lot lower torque, and the higher speed and the lower rotational inertia allows us to have a very high speed, high reaction time. The 4 different series that we make are the 35X, 45X, 50X, and then we manufacture a H36 series water brake. As I mentioned, the simple technology uses water shear, and we are increasing the temperature and flow of the water, or the flow of the water, and as the flow of the water increases through the machine, the power absorbed increases and the load increases accordingly. The benefit is it's an increased or low-cost technology. The negative is that you have to control that water, and the momentum of the water will decrease your performance. So steady state operation, it's a great technology. Eddy current technology is another machine that we manufacture a lot of eddy current brakes. The eddy currents that we power test manufacturers are air cooled, so the power capabilities are continuous up to 250 horsepower for engine testing or for motor testing. In addition, we also manufacture a large line of chassis dynamometers that utilize eddy currents as the loading technology. Getting into power test engineered solutions, AC Regenerative Technology has been prevalent for several decades now. It's got better and better as it goes, and the costs have decreased accordingly. The way that an AC regenerative system is used is it is using AC induction motors typically as the either motoring supply to drive or the absorbing load to load the output. In the case of the machine that you see on the right-hand side, we're actually combining some technologies and using a 2,000 horsepower input prime mover, which is an induction motor. And then the outputs, in this case, are actually dual eddy current absorbers to load the power. On the top left example, it's an AC loading only machine for testing engines. So the unit under test would actually be in this case, small diesel engine rated up to 500 kilowatts. And the output is a AC induction motor that uses the power electronics to turn that energy absorbed into electricity. We do a lot of different kinds of engine dynamometers in AC machines. The lower left-hand side shows a dual-ended 300 horsepower high-speed machine. This was designed to test a very wide range of engines, limited to 300 horsepower, but capable to 12,000 RPM. So it was designed to test everything from a UAV, a high-speed engine, through a small diesel. Regen systems are especially good for testing driveline components. In a typical powertrain, you're going to have transmissions and axles and drive shafts, lots of couplings in electric motor applications, or gearboxes in off-highway and power transfer pumping stations, etc. The best way to test driveline components, since you need to have a prime mover and an absorber, is for large power systems, instead of taking the absorbed power away and creating it by or loading it with heating water, we can actually take that load and create it into electrical energy, which is used to power the input prime mover. Similar application, what this slide is showing, is in a typical real-world application on the left-hand side would be a mining truck. And so if you wanted to test the mining truck transmission, in the actual application, you have a large diesel engine. This is showing a Cat C175-20 running a large mining truck transmission, which ultimately is just being used to drive the truck up and down and around in the mine. In the simulated world in the lab, to test that transmission, a great way to do it is utilize a large AC motor. The one on the right-hand side is shown as 5,000 horsepower capable. That'll actually couple to the transmission, and then the output would be another AC motor. The power is recirculated using the power electronics that we integrate, and the output load is used to power the input load, your input prime mover power. This ultimately just creates incoming power from the utility, or requires incoming power from the utility to overcome the inefficiencies of the test transmission. You eliminate the need for large amounts of diesel fuel and eliminate the need for large amounts of water that has to be cooled in the case of a water break load unit. AC Regen technology, fairly simply, I'll brush past this a little bit, but we're using a standard and or custom induction motor. That induction motor is being controlled by varying its frequency and varying its current to it to increase or decrease speed and increase or decrease torque. A quick overview of the AC Regenerative Technology. Benefits are that, if you look at the torque curve on the right-hand side, it's a typical example of a torque curve. You can get full torque, rated torque at 0 speed in the case of a vector duty induction motor. This allows us to create full, in this case, showing 2,400 pound-feet of torque at 0 speed all the way up through its base speed. The base speed is where the peak torque stops. The power is stabilized at its peak power, and then the peak power is available out to a decreasing power range. That is a typical torque curve of an AC dynamometer. It allows us to get full torque at 0 speed up to base speed, and then it's sized for the appropriate power that the unit under test needs to be run at. Benefits are it's what's called 4-quadrant, so we can actually motor or drive as much as we could absorb. This helps in fast transients where you need to have an engine or a unit under test see significant accelerations or decelerations. And it also allows us to blow or cool and take that power that's absorbed and turn it into electricity, eliminating the need for cooling water. Several weaknesses. The obvious one is the affordability, because ultimately you have a large AC induction motor that also needs the appropriate power electronics. So the cost of AC dynamometers are sometimes more than 3 or 4 times, if not more, than what a water break dynamometer would cost. So depending on the benefits that you get from the more efficient cooling and the driving 4-quadrant torque capabilities, sometimes it can't be justified. Which brings us to the typical decision factors. In this case, I'm showing engine only. Water break dynamometers are almost always chosen when you're exceeding 1,000 horsepower. With the cost of power electronics reducing year over year, that power level is increasing, but it's still typical rule of thumb. Anything over 1,000 horsepower, unless you really need to have the regenerative technology, it's hard to justify. Eddy current dynamometers are usually justified if you have to have some higher speed, you have enough water cooling, and you need a low inertia system. Eddy current dynamometers are faster response to control than a typical water break, because ultimately for an eddy current you're controlling electrons, whereas with the water break you're controlling water, which has more inertia. An AC dynamometer should be chosen when you need to have that 4-quad motoring and absorbing power. If you need to crank an engine and don't want to test the engine with its starter, and again, this is all an example of engine dynamometers, not necessarily powertrain dynamometers. Powertrain dynamometers are a different discussion on the whole cost-benefit ratio. Typically, there's a lot of different benefits to having 4-quad, including being able to test frictional data. If you have to have an engine test in order to meet the EPA FTP heavy-duty emissions standards, which requires motoring, then you'll need an AC dynamometer. And then there's also large benefits to not having to have a cooling tower. In power tests and most AC engine dynamometer controls, you're going to have in our case, we use PowerNet Workstation as the main control system. That is basically communicating to the VFD, which is controlling the speed and torque that's requested from the control system to the dyno. So it's controlling the current and frequency. You've got a commander computer that is going to be your operator interface. And then you've got various power supplies for fuel measurement systems. And if you have emissions analyzers, there's all kinds of accessories that Workstation can communicate with in order to gather the data that you need to for the engine that you're testing. This is showing a couple examples of power electronics just to understand where those extra costs come in. On the left-hand side is a simple little 500 kilowatt AC dynamometer, but you can see that that control cabinet is about 110 inches wide. So it's a significant amount of power electronics that are used to control a 500 kilowatt unit. The machine on the right, believe it or not, Alex, is almost 6 feet tall in that background there. That's a medium voltage in order to keep the current down, 3,000 volts, 5,000 horsepower, dual motor, fully line regenerative AC test system in order to test powertrain components. And then on the left-hand side, just to show another example of trying to put the power electronics somewhere, we had to do a folded VFD design for a dual motor 2,000 horsepower common bus system. When I say common bus system, this is a good example slide to explain common bus. For drivetrain components, we have to recirculate the absorbed power back into the prime mover, and we do that with our common bus power electronics. You don't have to have full line regeneration because there is no external power source other than the motors. So you don't have to worry about putting power back onto the grid like you would with a AC engine dynamometer. So ultimately we are converting the power from 60 hertz or 50 hertz line power to the frequency that we need to for the motor speed for the input power. The output power is absorbing that torque, creating the appropriate, actually converting it to DC, and then that DC bus is charged and supplies power to the prime mover. So ultimately the DC bus maintains its voltage level, creating equality between the input and the output motors. Some benefits of AC technology are, again, it significantly reduces power consumption, which is not needing water, and not needing to have that input power just consumed. You're actually recirculating it. We can operate full torque at 0 speed as well as have motoring, uphill and loading downhill simulations. And then our standard control system can actually control up to 8 motors for agriculture applications where you're testing various wheels on a multi-wheel vehicle or PTOs or various power takeoffs. This is showing typical experience in how our process works in engineered solutions. We not only do AC regenerative systems, we do a lot of custom hydraulic test systems, various custom chassis dynamometers, but in general, we test a lot of different things that the standard power test equipment can't do. So with that said, that concludes what I wanted to talk about. And if anyone has any questions, feel free to submit them via email. There's my email address, and we will try to get back to you as soon as possible. If you've got an application that we can help you out with, we love to be challenged.
Hey, Rob, we actually had a question come in a little earlier from James. Thanks, James, for the question. Can you go back to the benefits slide? It was addressing when the power, the bullet point significantly reduces test lab power consumption. The question was, at what scale is that really relevant? I mean, what testing applications makes AC Regen the most viable solution?
Well, to answer that, I need to know what they're testing. If they're testing an engine, which automatically you have to push power back onto the grid if you're using AC dynamometers, because the engine is supplying the power source and the dynamometer is just the load. So the regenerative power can actually be used in a factory or even in a lab setting to power the rest of the facility. We've got small customers that are testing and actually having their electric meter run backward. The benefit is, in some cases, the utilities will actually pay for that power. In other cases, the utility just simply doesn't charge you for the power that it would take to test. If you were testing with a water break dynamometer, you'd have to take that water that you're using to load your engine, in this case, and cool that water or just dump it down into the sewer. So reducing power consumption can be looked at in various ways. If you're testing a drivetrain component, you have incoming power and you have an outgoing load, and the only power needed from the utility would be the inefficiencies of the test article and the test stand, which, depending on the test article, if it was just a drive shaft, there is no inefficiency, and so the test stand would lose about 5 to 10% of its power. So if you're testing 5,000 horsepower and continuously loading that, the incoming power would be maximum 500 horsepower from the utility, whereas if you had non-regenerative technology, you'd be losing all 5,000 horsepower.
Okay, thank you. I hope that answered the question. To all the viewers, if you go to the chat feature or the questions feature, you can submit your own questions. Rob will hang on the line for a few extra minutes, ready to answer any questions that you might have. Otherwise, as he mentioned, feel free to reach out to him at robk@powertest.com, and he'll be happy to consult with you on an individual basis of any further questions that you might have.
You don't want to actually send it to powertest.com. I think pwrtst.com would be the email that gets to me. We don't exactly know where powertest.com would go.
That's correct. That email is on the screen. All right, and that concludes our presentation for today. As Rob mentioned, he'll be online for a few more minutes if any chats or questions come through. Other than that, we thank you for your attentiveness and look forward to continuing our webinar series next month with a webinar on eddy current chassis dynamometers and where they're most applicable. Thank you all for your attentiveness, and have a great day.